Welcome to another exercise on the Simplex algorithm. Here we have a slightly longer text exercise with the general information going as follows. Mining Corp owns two mines which provide them with two types of ores of different quality. Each ton of ore, type 1, contains 20% copper, 20% zinc, and 15% magnesium. Each ton of ore type 2 contains 30% copper, 25% zinc, and 10% magnesium. Ore type 1 costs $90 per ton to mine, while ore type 2 costs $120 per ton. Mining Corp would like to mine enough ore to extract at least 8 tons of copper, 6 tons of zinc, and 5 tons of magnesium in the least costly manner. Based on this, we have two tasks. First, reformulate or formulate the respective linear problem. Then, based on this, determine the optimum quantity of ore to be mined in both locations. Well, let's start with part A. If we start with formulating this in a mathematical manner, and as a problem, we first have to go with the objective function. However, we have a good indicator what this is about because it says in the least costly manner. So we want to minimize costs. Costs we also have given here, $90 per ton of type 1 ore, $120 per ton of type 2 ore. So we can set our two decision variables as x1 being the amount or the quantity of type 1 ore to be mined, x2 the quantity of type 2 ore to be mined. Then our objective function results as minimize 90 times x1 plus 120 times x2, which is this. Well, 90 and 120 are quite large numbers to use in our table for recalculation, so we can simplify all of this a little bit by dividing the whole equation by 30. If I do this, I get as a result 3x1 plus 4x2. Well, this will make calculation a bit easier, but I have to remind myself that I have to do the recalculation once I arrive at the optimal solution in the end. Well, but this is later on. Let's continue with our constraints, which come next. And the constraints result from the minimum amount of, well, copper, zinc, and magnesium they want to extract. Well, 1 ton of type 1 ore has 20% copper. So 0.2 x1 results from type 1 in copper, and type 2 has 30% copper, so for each ton I have 0.3 tons of copper. This can be used in the third way to say, okay, 20% of each ton I get copper with. Each type 2 ore yields 30%, so 0.3 tons of copper ore. Those two added up is the total amount of copper which I get from my type 1 and type 2 ores. And this should be larger than 8 tons. Well, again, as before, 0.2, 0.3, they are not nice to have in the calculation table. So if it's possible, we might try to avoid working with fractions or decimals. So to make our life easier here, we can multiply the whole equation with 10, giving us this result. Well, this was copper. In a similar way, we can go about zinc. Zinc, we have 20% in each ton of type 1 and 25% in each ton of ore type 2. So we have 20% of x1 plus the amount from the ore type 2 which we get, so 0.25 times x2. This should be larger than the required 6 tons of zinc. Again, to avoid having here some kind of decimals, we can multiply all of this However, as compared to the first one, we multiply here with 20, giving us this constraint. Well, that was the second one. Then we are left with magnesium. Here we have 15%, so 0.15, and 10%, so 0.1. And this should be larger than 5 tons. Again, we want to reformulate this. Ideally, similar to the second one, we multiply this with 20, giving us this reformulated constraint. And of course, we can only mine positive amounts of ore, so we have to add non-negativity constraints, x1 and x2 being larger or equal to 0. Well, so far so good. That's about it with the problem formulation. We're going to use the shortened version in our calculation of the optimum of this problem. So I'm going to copy this, then I'm going to generate a calculation table out of this. So first off, for each decision variable, I'm going to introduce one column. So I have one column for x1, one column for x2. For the objective function, I'm going to insert this z row. And then for each constraint, I'm going to insert one additional variable with one row each. So the first, second, third constraint. Well, so much for the frame. Now we have to insert the numbers. Since this is a minimization problem, we can take the coefficients of the objective function and just insert them here into the table. Then all the values up here have a value of 0. Variables up here have a value of 0. So x1, x2, we set equal to 0, insert this in the objective function, and get a value of 0 for the starting solution. Then we have to consider the constraints. To put them into this table, we have to reformulate them in a way that they always read smaller or equal to. Well, none of those actually do it. So what we have to do is multiply each of the 3 constraints with -1. This will turn around these inequality signs. And for all the other numbers, it will just put a minus in front of them. So for x1, for the rest of the x1 column, we have -2, -4, -3. For the x2 column, we have -3, -5, -2, those ones. And on the right-hand side, we have -80, -120, -100, those ones here. So this gives us our initial table. And with this table, we first have to check whether this starting solution is actually a feasible solution. For this, we're going to check the values here on the right-hand side. We see, well, they are all negative. This tells us that our solution is not feasible. If it were feasible, then those values would be positive or 0. Well, what can we do about this? We're going to select one row where we have the absolutely largest value. That's here, the -120. So x4 row becomes the pivot row for recalculation. In this pivot row, we're going to select a negative number. So here we have 2 choices. And ideally, we're going to go with one number here where in the objective function we have positive value. Well, both qualify again. So what can we do next to make a decision? Well, we're going to divide the values up here by the values down here. And then select the one with the absolutely largest as well. Here we have 3 by 4, so 0.75. Here we have 4 by 5, 0.8. So we go with this column. So x4 pivot row, x2 pivot column, giving us a pivot element of -5. So we can do our simplex transformation with this new pivot element of -5, resulting in this table. So how do we get to this table? Well, first we exchange variables in pivot row and column. For the pivot element, we go with 1 divided by pivot element. For everything else in the pivot row, we're going to divide it by the pivot element, so by -5, giving us these values. Everything else in the pivot column is divided by the negative pivot element, so by +5. This divided by +5, by +5, by +5, giving me these values. For all other values, so this one, those two, and that one, we're going to have to use a rectangular form. Rectangle form or scheme, what does this mean? Well, we consider the value we want to change. For example, here the 3. And we consider it as one corner of a rectangle. Pivot element being the opposing corner of the rectangle. So for this, we get this rectangle here. Then we go with the calculation, original element minus this corner times that corner divided by pivot element. So here, 3 minus 4 times -4 divided by 5. Minus, 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 3 minuses, 2 cancel each other out, we are left with 1 minus. So 3 minus 16/5. Well, this is 15. 6, if I subtract 16/5, I'm left with -1/5 or minus 0.2. Well, the same scheme I can apply to all other values as well. For example, here I have these values, this rectangle. So 0 minus 4 times -120 divided by -5. Again, minus, 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 3 minuses reduced to 1 minus. This times this divided by this is 96. So here we get -96. This goes similar for all the other values. So for this 2, we have this rectangle here. So this minus this times this divided by this. For the -3 down here, we have this rectangle. So this minus this times this divided by this. For the -80, this rectangle. So this minus this times this divided by this. And for this one, we have this rectangle here. If we do all the recalculations, we get this table here. Well, we can take a look first. Have we arrived at a feasible solution? No, we did not, because we still have 2 negative values here. So again, we're going to select the row with the absolutely largest negative value, which is this one. Select this as pivot row. In the pivot row, take a look at the negative elements, so both qualify. Then select one where ideally up here we have a positive value. Well, both do not qualify. This is negative, so only this qualifies, giving us -0.4 as the new pivot element, because this will be our pivot column. This is the pivot row. So in the next slide, we continue then with the simplex recalculation for this pivot element. We do this, again, we change the variables in pivot row and column. Pivot element, we have 1 divided by pivot element. Everything else in pivot row is divided by the pivot element. So minus 1.4 divided by minus 0.4 gives this. Minus 52 divided by minus 0.4 gives 130. And everything in pivot column is divided by the negative pivot element, so by 0.4. If I do it, I get these values here. Again, for all other values, I'm going to use this rectangle scheme. So for this value here, I have this rectangle. So this value minus this times this divided by pivot element. For this one, this rectangle, this minus this times this divided by this. If I do all the recalculations, I will end up with this table. And if I look to the right here, I see all the elements are positive. So I have finally arrived at a feasible solution, meaning I can now start my normal simplex process. Normal simplex process means I start with selecting pivot column first. For pivot column, I take a look at the values here in the objective function row, and I select a column where I have a negative value, or in other words, we have the largest, absolutely largest negative value. Well, here there's only one chance, so x1 becomes my pivot column. In the pivot column, I'm going to take a look at all the positive entries. Well, all three qualify, they're all positive. And then I'm going to divide the right-hand side value by the respective value here. Do this 70 by 2.5, 50 by 1.5, 130 by 3.5. And out of this or these three quotients, I'm going to select the row where I get the smallest result. This will be the case here for 70 and for the x3 row. So this becomes my pivot row. So this is pivot column, x1 is pivot column, x3 is pivot row. So the 2.5 becomes my pivot element. So in the next slide, I'm going to do my transformation using this one as pivot element. So with this, I can do the transformation. I'm going to switch variables x3, x1. For the pivot element, I'm going to go 1 divided by pivot element. And for everything else in the pivot row, I divide by pivot element. Everything else in pivot column, I'm going to divide by minus pivot element, giving me this column and that row. So far, so good. So I have a positive value here. So let's next check if this value also is positive, because then I know I will have arrived at my optimal solution. So I'm going to go with this rectangle. I have 3 minus 3 times minus 1.5 divided by 2.5, giving me as a result 0.2. Well, if I have 0.2, this is positive as well, so I know I have arrived at my optimal solution. If I have arrived at the optimal solution, I do not need the values inside of this table here. So those values do not matter anymore. So I do not have to calculate those which I have not yet calculated, like those two. I could also theoretically leave this value because this is just a constraint. Well, however, if I do calculate all the other values here, for this value, I have this rectangle, so this minus this times this by this. For this value, I have this rectangle, so 50 minus 70 times 1.5 divided by 2.5. And for the 130, I have 130 minus 70 times 3.5 divided by 2.5, giving me the values as I see them here. Well, this is, as I said, the optimal solution. So the values up here, they have a value of 0. The values of variables here, they have the values as seen here on the right-hand side. So in other words, my optimal solution is x1 is 28, x2 is 8. So I should mine 28 tons of ore type 1, 8 tons of ore type 2. This will result, and now I have here the costs. Well, with minimization problems, I will always get a negative value. So first off, I can erase this minus. So of cost of 116. But well, as I said, 116, this is taken into consideration that I have simplified my objective function. If you remember, I divided the objective function by 30. So I have to multiply this result again by 30. So the actual costs are not minus 116, but as I said, disregard the minus, multiply with 30. So the costs are $3,480. Well, that's the optimal solution, but I can get some additional information out of this table. As I said, all the variables up here are 0. There are 2 variables here, both of them considering my constraints. This was for copper, this was for magnesium. So in other words, if they have a value of 0, this means that those constraints are fulfilled with equality. So I barely get the required amount of copper and magnesium if I buy this many types of ore 1 or 2. Mine, not buy. This value down here, this was zinc. This tells me that if I mine this amount of ore type 1 and 2, I will have more zinc than I need. So I have some buffer here. So I get a total of this much of zinc more than I would actually require with the requirements given. And well, that's then everything I could get from this table. This is the optimal solution. This brings me to the end of this session. So I hope you enjoyed it. I say goodbye and see you next time.